You know that feeling when you get to see something that was previously hidden, something you'd only ever glimpsed before?
Huh.
Like pulling back a curtain and suddenly seeing all the intricate machinery working away?
Yeah, I know what you mean.
Well, imagine that, but like scaled way up to the biggest thing in our solar system, the sun.
Right.
Specifically, we're talking about its mysterious, superheated outer atmosphere.
The corona.
The corona. Yes, that's definitely one of the sun's, well, biggest enigmas, isn't it?
It really is.
It's this incredibly dynamic place, millions of degrees hotter than the surface right below it.
Which is just wild when you think about it.
Exactly.
Yeah.
And it's the source of those huge eruptions, the ones
Yeah.
that drive space weather. But yeah, for us here on Earth, getting a really clear, detailed look, almost impossible most of the time.
You basically only see it during a total solar eclipse, right?
Pretty much. That's when it's most obvious, yeah.
And that's been the core of the challenge and the fascination, I suppose. We've had these massive fundamental questions for, well, decades now. Absolutely. Like,
Yeah.
why is the corona so incredibly hot? What are the precise forces driving all that solar activity and the space weather it kicks off?
Big questions.
Huge. And until very recently, let's say the resolution of our observations just wasn't good enough. We couldn't really get down to the fine-scale physics we think is causing it all.
Okay, so that's what we're diving into today. A major technological breakthrough that is apparently revealing the corona like never before.
That's the plan.
We've been looking at sources detailing a study published in Nature Astronomy, scientists from the NSF's National Solar Observatory and the New Jersey Institute of Technology. And it really sounds like it's changing the game.
It really does. And, you know, the main reason it's been so hard to get that clear view, it actually comes down to our own planet.
Earth's atmosphere, right.
Exactly. Our atmosphere causes blurring, distortion. Scientists call it seeing. Yeah. It just severely degrades the images we get from telescopes on the ground.
Right. And we have used adaptive optics, that technology, for years on solar telescopes, haven't we, to get better views of the sun's surface?
We have, yes. And they've gotten really good for the surface, pushing pretty close to their theoretical limits there.
But not for the corona.
But, as the source points out, that standard adaptive optics tech, it hasn't worked so well for observing the corona itself. You know, the faint stuff beyond the bright edge, the limb of the sun.
Ah, okay. So looking at the bright surface is one thing.
It's a very different challenge than trying to see the much, much fainter corona just next to it. The atmosphere turbulence messes with the light path differently, and, well, the standard systems just weren't built to effectively fix the distortions affecting that specific coronal light.
Okay. So what's been the actual consequence of that limitation for studying the corona, I mean?
Well, the consequence has been pretty stark, really. The resolution we could get of coronal features, anything outside that bright solar disk, it's been stuck at around 1,000 kilometers, maybe even worse.
1,000 kilometers.
Or worse, for something like 80 years.
80 years, wow. We just couldn't see the fine structure.
Exactly. And a kilometer-scale blur on something as dynamic and potentially fine-structured as the corona.
Yeah.
Well, that's a huge handicap if you're trying to figure out why it's millions of degrees hot.
No kidding. Okay, so what is this breakthrough technology, the one that's finally getting past this long-standing problem?
It's a new system. They're calling it coronal adaptive optics, or Cona for short.
Cona, okay. And where did they put this Cona system to the test?
It's installed at the 1.6-meter Good Solar Telescope. That's in California, operated by NJIT.
Gotcha. So how does Cona actually work? How does it fight that atmospheric blur specifically for the corona? Is there a simple way to picture it?
Well, think of it like this.
Mm.
It uses a special mirror, the formable mirror, that continuously reshapes itself, and it does it incredibly fast, 2,200 times every second.
Whoa.
It's analyzing and counteracting the image distortions from the air turbulence in real time. The source used a pretty good analogy, actually.
Oh, yeah.
It said it's like a pumped-up autofocus and optical image stabilization in your smartphone camera,
Okay.
but correcting for the errors in the atmosphere rather than the user's shaky hands.
Ah, okay. Constantly adjusting that mirror shape to keep the image sharp, even though the air above is messing things up. Makes sense.
Precisely.
And what kind of improvement did this actually deliver? What's the result?
The direct result is, well, it effectively removes that atmospheric blur that plagued previous coronal observations. And the impact, it's dramatic. It delivers images at 63 kilometers resolution.
63, down from 1,000.
Down from 1,000 or more, yeah.
Yeah.
And that 63 kilometers, that's actually the theoretical limit of the Good Solar Telescope itself. It can't physically see any sharper than that.
So it's hitting the telescope's absolute limit for sharpness, but for the corona, that's incredible.
It really is. Thomas Ramelli is the NSO chief technologist, involved way back with the first adaptive optics for the sun's surface. He notes that this Cona system, quote, closes this decades-old gap,
Yeah, I'll say.
boosting the resolution by a factor of 10 compared to those previous views of coronal features beyond the limb.
A factor of 10 improvement. That's just huge. So what does that look like, going from a 1,000-kilometer blur down to just 63 kilometers? What hidden details are popping out now with this new clarity?
Oh, the observations are truly stunning. They're seeing detail that's just unprecedented. Because we can see so much more clearly now, we're already observing phenomena. I mean, things happening with a level of resolution that just wasn't possible before. And it's giving us new clues about how the corona actually works.
Okay, like what? Give us some examples of the specific things they've captured.
All right, so one major area is seeing solar prominences better. You know, those huge structures of plasma, they loop out from the surface. You often see them during an eclipse.
The big loops.
Yeah. With Cona, they're revealing rapid, fine, turbulent flows inside these prominences.
Inside them.
Yes. You can actually see this dramatic motion shaped by the sun's magnetic field lines. Seeing that internal churning, that kind of detail at this scale, it's completely new.
Wow. So not just the overall shape, but the weather inside the prominence?
Sort of, yeah. And what else? Well, they observed a really fast stream of plasma, something scientists call a plasmoid.
A plasmoid.
Yeah, the video apparently shows it forming and then collapsing at almost 100 kilometers per second. Super fast.
Whoa.
And Vasil Yurkishin, one of the co-authors on the study, commented on this one specifically. He noted it's likely the first time such a stream has ever been observed like this.
No way.
Right. And its physical explanation, not clear yet. He said, these are by far the most detailed observations of this kind, showing features not previously observed, and it's not quite clear what they are.
Huh.
That's the sign of a real discovery, right?
Yeah.
Seeing something totally new, unexpected.
Seeing something that actually makes you scratch your head and say, what is that? That really is exciting. What about coronal rain? I've heard of that.
Coronal rain, yes, another fascinating one. This is basically where hotter plasma way up in the corona cools down, condenses, and then falls back towards the sun, kind of like rain, but following the magnetic field lines.
Okay.
So, the new views from Cona show incredibly fine strands of this cooling plasma falling down.
How fine.
Well, Thomas Shad, an NSO astronomer involved, highlighted a particularly surprising detail from these images. He said the strands of this rain can be narrower than 20 kilometers.
20 kilometers, narrower than 20 kilometers on the sun, which is what, 93 million miles away?
Exactly.
That level of detail, it just blows my mind.
It's pretty amazing, isn't it? And Shad really emphasizes why seeing this matters so much. These findings offer new, invaluable observational insight that is vital to test computer models of coronal processes.
So we can check if the computer simulations are getting it right.
Precisely. Our current computer models trying to explain, why the corona is so hot, how it all works, they can now be tested against real observations at these incredibly fine scales, see if they match up. And the source also mentioned, just for context, that these videos were taken using a specific type of light, hydrogen alpha light from the plasma, which corresponds to certain temperatures, and the color you see in the images. That's artificially added based on the light's intensity, just to make the structures easier to see.
Got it. Okay, so we've seen prominences with internal churning, these mysterious fast plasmoids, super fine coronal rain. Let's explicitly tie this back to those big questions we started with. How are these fine-scale observations seeing things as tiny as those 20-kilometer plasma strands? How is that supposed to hold the key to solving, say, the coronal heating mystery?
Well, the hypothesis, the main idea among scientists, is that the structure and the dynamics of this cooler plasma stuff like the rain, the flows and prominences at these now visible small scales, they're intimately linked to how energy gets transferred and dissipated throughout the corona. And that, potentially, explains why it's millions of degrees hotter than the surface. Understanding how these fine strands of rain behave, or the turbulence inside prominences, that could reveal the actual mechanisms that are dumping these vast amounts of heat into the corona.
So the answer might not be in some single big process, but maybe hidden in all these tiny, intricate details and motions we just couldn't see before.
That's the working theory, yeah. That's what many scientists believe. And there's a vital link to space weather, too, of course.
Right, you mentioned that earlier.
Understanding these small-scale dynamics,
Yeah.
how plasma behaves in these fine structures, how energy builds up and then subtly releases. It's absolutely crucial for understanding the larger eruptions.
Like CMEs, coronal mass ejections.
Exactly, like CMEs, which throw massive amounts of plasma out into space. Those are the events that drive space weather, the stuff that can really impact our technology here on Earth and in orbit, affects power grids, GPS, satellites, you name it.
So seeing the building blocks in detail helps understand, and maybe even predict, the bigger, more powerful events.
That's the hope. Better understanding should lead to better prediction down the line.
It really sounds like this Cona technology is, well, lifting the veil on fundamental processes we could only really theorize about before. What's next? What does the future look like for this?
Yeah, this definitely isn't the end point. It really feels like the beginning of a new era for solar physics. Dirk Schmidt, the NSO scientist who led the Cona development, he flat out calls it a game changer.
A game changer.
And he says, there is a lot to discover when you boost your resolution by a factor of 10.
I can only imagine. Just a flood of new data, new insights coming.
Absolutely. And the team, they now know how to overcome that key resolution limit, the one imposed by the lowest part of our atmosphere, the troposphere, specifically for these observations beyond the solar limb.
So they've cracked it.
Seems like it. And the obvious, really exciting next step is to apply this coronal adaptive optics technology to the world's largest solar telescope.
Which is?
The 4-meter NSF Daniel K. Niue Solar Telescope, DKIST, in Hawaii.
Okay, taking this tech from a 1.6-meter telescope to a 4-meter one, that means DKIST will be able to see details even smaller than 63 kilometers, right?
That's exactly right.
Yeah.
It'll push the boundaries of what we can resolve even further, see even finer details. Wow. And the prediction, naturally, is that this kind of transformative technology is likely going to be adopted at observatories all around the world, now that its success has been proven so dramatically.
Makes sense, if it works this well.
Right. Philip R. Good, he's a distinguished research professor at NGIT, also a co-author. He states it very clearly. He says that with coronal adaptive optics now operational, it, quote, marks the beginning of a new era in solar physics, promising many more discoveries in the years and decades to come.
A new era. It really feels like it. This technology is genuinely lifting the veil on the sun's corona, showing us these previously unseen details that are vital for understanding how our star works, how it affects us through space weather, stuff we couldn't have dreamed of seeing clearly before.
Yeah, and what's kind of fascinating here, just pausing to think about it for a second, uncovering details as small as those 20-kilometer plasma strands, right, on the sun, 93 million miles away. And that can fundamentally change how we understand phenomena powerful enough to actually affect technology right here on Earth. That connection is amazing.
It really makes you wonder, doesn't it? Thinking about, what other universal connections might be out there between these tiny microdynamics and huge macro events, connections just waiting to be revealed, maybe, simply by improving our ability to see things more clearly.